Introducing industry-first application-specific standard product based on asymmetric half-bridge flyback topology with Infineon's latest hybrid flyback controller, XDPS 2201, to enable ultra-high-density charger design. It consists of a few major building blocks: a main stage and a PWM controller on the primary side, a rectification and communication protocol on the secondary side. XDPS 2201 converts and delivers power over an isolated barrier in an efficient and safe manner. Targeted application includes smartphone charger, adapter, and USB PD charger. Bill of material savings and ease of design with an integrated high-voltage startup cell and high-side MOSFET gate driver to yield a potential saving of up to 20 external components. Multi-mode operation across varying load and line input conditions delivers high peak and average efficiency. Simplified and low-cost transformer design with a single auxiliary winding to support variable output voltage requirement. Infineon has developed a USB PD charger solution housed in an ultra-compact PCBA form factor. The solution supports a maximum output power of up to 65 watts, delivering a class-leading power density of 31 watts per cubic inch. As a leader in power semiconductor, the 65-watt solution incorporates CoolMOS, OptiMOS PD, communication protocol controller, and hybrid flyback controller XDPS 2201 to deliver a high efficiency of up to 93.8% to miniaturize your next charger design. For more information, please visit our website www.infineon.com/XDPS2201.
So my name is Arif Nurrahman. I'm currently, as has been introduced by the chair, I'm currently a senior power electronic engineer from FSP Technology. The FSP Technology and FSP Group, it's basically the same. And today I'm going to present about basically trying to understand how a charge mode controller is implemented in a IC. And for this case, I'm using the NCP4390 for my use case, and then how I can make the model of the IC. And to be specific, in this case, I'm using it modeling in the Qspice. And then I'm also pretty active in various online forums. So you can find me in LinkedIn, or you can also find me in a Qspice forum, and then for some of my Qspice work, I also uploaded in my GitHub, including this very presentation. So if you look at the chat, you can see that it disappeared. Okay. So basically, for today's presentation, you can find the presentation material in my GitHub page. And so you can access the file in this link for this presentation, including all the simulation material that I'm going to present here as well. And okay, let's move on. And however, this presentation will not be like your typical presentation like in the seminar. So I will also open my simulation a few times, and we can look at the presentation and the simulation back and forth. All right, so a little bit of a disclaimer. I'm working for FSP. I have no affiliation with Onsemi, who makes the NCPIC, and I'm also not affiliated with Corvo at all. And then Qspice is a variant of a Spice developed by Mike Engelhardt and his team. And this is solely developed for Corvo as a primary distributor for this. And you can get the software freely from the Corvo website. And then, yeah, the material I present here is basically contain no confidential information belong to any of my employers. Okay, so a little bit of introduction. So when we are talking about LLC converter, the most common implementation for LLC converter is using a direct frequency modulation, which is, for example, one of the most popular is this IC L6599. This one is from ST Micro, or from the TI, you can also find this IC UCC25600. And then in the last few years, there have been another popular different kind of IC that are developed by a few manufacturers. For example, onsemi, they have NCP4390, and also they have another variants, which is basically pretty much similar, or from TI, and also from MPS, and TEA this one is from, what's it called? NXP. Okay. So, okay, later we can move on about some of the benefit and all the benefit of using the charge mode control. And then why do we need to make a simulation? Basically because prototyping and hardware testing takes a lot of time and also takes a lot of money. The money itself not just come from the prototype cost itself, but also comes from the time of the engineering, from the engineer to work on these issues. And then simulation can help us to get us closer to the desirable result faster and also cheaper because, just run in your computer. And then, of course, the problem about running a simulation is we have to make sure that you have good enough accuracy for your model. And however, you need to make sure that you can find the balance between the complexity and the accuracy, because of course you can make 100% accurate model if you have time for that, but the development time itself takes a lot of time. And second is it may takes a lot of time to run in your computer. And meanwhile, your computer, I believe, will not be as powerful as the one that is owned by those big manufacturers. So yeah, so you have to be wise about how to create moderate complexity IC models. And then Qspice, basically the reason why I'm using Qspice is number one, obviously, is free. And number two, it supports C and Verilog modeling. So in case you are familiar with LTSpice, basically, if you want to make any model, you have to work with the available blocks there. You can use, I don't know, RC components, or you can also use some amplifier, some variable voltage source or behavioral source or that kind of thing. But the thing is, you have to find a way to implement your models using blocks. And for digital implementation, it can be very tricky. So the good thing about Qspice is it now supports the C block, so we can directly write the C code to model our behavior that we want to simulate. Or if you are more like an IC guy, then you can also use Verilog. And last thing is it's crazy fast. Okay. Okay, so some general overview of the IC. So this is the NCP4390. And basically, NCP4390, even though this is an IC, however, internally, it is implemented using a mixed mode approach. So it's not really an analog IC, although from the outside, we can interface with the IC by using resistor and capacitor, but internally it's actually a mixed mode. So some part of the system is implemented by using digital approach, while some other parts is implemented using analog approach. Most likely the part that are implemented using digital approaches are for the PWM generation, because that's pretty much a digital thing. And also for protections, because protection logic, if you are writing in the code, it will be very simple, but if you are going to implement with hardware, it's also going to be pretty messy. And the other thing is also for this part here, you may see the compensation or cutback signal generator. So basically that is for low power operation. And for the result control and everything. But for the main power conversion controller itself, it's still in analog mostly. Okay, so what the hell is charge mode control? So basically, charge mode control compared to charge mode control compared to the sibling of the direct frequency modulation, the difference is for direct frequency modulation, the way that those kind of LLC controller work is by adjusting the frequency directly from the output. So you have a compensator where your compensator can detect if your output is higher or lower than your reference, and then from that controller it directly tells how much is the frequency that the IC needs to operate on. However, the difference between that and the charge mode control is the charge mode control, the controller does not tell how much is the frequency that it needs, but the controller tells how much charge needs to be delivered to the load. So in one of the most common ways to explain the difference between charge mode control and direct frequency modulation is charge mode control basically will be analog to current mode control in a PWM converter. Meanwhile, for the direct frequency modulation, it will be analog to the voltage mode control. And as many of you may be already aware, that current mode control in a lot of fashion is much more nicer to work with. And later we can also see why it is a lot nicer. Okay, so next is Qspice. Okay, Qspice is developed by Mike, and then primary feature is, as I already mentioned earlier, it is free, and then it is the only spice according to him, but according to Mike's own word, it is the only spice with native ideal switch model. So if any of you are aware that the reason why there is a simulations like PSIM or Plex is basically those kind of simulation, they deal well with the switching element. So basically something that can just change from on to off in one simulation time step. However, by the original design, Spice actually does not support that. So back when Mike was working in the LT Spice, he deals a lot with how to make sure that the simulation can still remain stable, even when you are going to use the simulation for switching with the switching transistors. And so basically, because LT Spice is a older software, so Qspice is the newer software developed by Mike, and because it's a new one, so he's according to his own word, he modified this implementation radically so that it is much more capable to handle. It is now natively capable to handle instantaneous switching, and then it also supports the mixed mode simulation with C blocks while it's free. The other software, the other Spice that I'm aware is Qspice. Qspice also supports C block, but of course Qspice is a proprietary software, and it's also commercial software, and it's natively fast. And if you have some programming capability, it can go insanely fast. So I have an example here on the right side, the bottom right side here. This picture is a little bit small, but this is a totem pole PFC. And then for the whole simulation, where it takes 2 seconds for my whole test here, as you can see here, it only takes me 27 seconds. Of course, you cannot get this performance if you only using the native blocks, but if you understand how to play with the C blocks, then you can reach that kind of performance. And then because I spend a lot of time working with Qspice, I also implement frequency response analyzer that later I also show you. So basically, this is a way to analyze the circuit behavior using frequency domain. So I implement this magic block on the big block on the right side here, and this block can help us to analyze the frequency response characteristics, so we can get the magnitude and phase of the circuit. Okay, so next we can move on to the modeling approach. So basically, because my job is a power supply engineer, power electronic engineer, so my big part of my work is to make sure that my system works well and also stable. And so a lot of my work will be related on the critical function that I do really care on the normal operation. So that's why in this presentation, I will be limiting myself to compensator part, soft start, charge mode control implementation, VCO, bus mode, and however, a few other things are not implemented. For example, the advanced protection, low power operation mode, and SR controller. I implement a very simple, very basic SR controller, but it's not going to be exactly the same as the one that is actually implemented in the NCPIC. However, that is fine because the SR, the synchronous rectification, does not affect the transient performance of the IC. And then, of course, when we are going to make the simulation, we have to start simple. If it's function independently, and later slowly you can combine all the function and test each part. And also at the end, you can test the whole function. Okay, so next this is a control overall. And you can access the blocks in this link. Oh, yeah, you should already be able to access that link anyway. So, all right, so this is the basic block diagram of the IC. Yeah, you are not familiar with working in this kind of thing, it may look pretty confusing, but luckily they already prepared a rather simplified diagram where basically the core of the charge mode control. How to hide this thing? How to hide this thing? Okay, I don't know. So basically, the core of the charge mode control is we want to control how much charge is being delivered from the primary side to the secondary side. So the reason why LLC do not do current mode control but instead they do charge mode control is because current in a resonant converter is sine wave. And because it is sine wave, and if, for example, compared to the PWM converter where the current is a triangular wave or trapezoidal, if you want to call it that way, for the triangular waveform, then you just need to set an upper limit. Then once you reach the upper limit, then you turn off the MOSFET. However, for this kind of sinusoidal current, then if you just set the upper limit, for example, you set the upper limit at this point, yeah, of course, you can turn off the MOSFET. However, if you set the upper limit at this point, then the MOSFET will turn off much earlier than you intended to. So basically, using current for to control the turn off time of the MOSFET is not going to be the brightest idea. However, luckily, some smarter guys, they decided, okay, if we cannot use the current, then what else can we do? So then they decided, okay, maybe what is the integral of a current? The integral of a current, which is a sine wave. The integral of a sine wave is a cosine. And if you look at this picture here, the integral of this sine wave becomes almost like a triangle, right? So because this one has monotonous nature, where it just keep going up, it doesn't really going down again. So this one will be much more consistent if you want to use the signal to turn off your switch. So that's why then, okay, they decided maybe we can try to use this one, and turn out the result is much, much better. So yeah, so basically from this whole diagram that I come out with the simulation model for this IC as the one you can see on the right side, right? So, okay, let's start something simple. Number one, we can start with the compensation and soft start. All right, so for the compensation here, number one, you see that this one, for the compensator itself, it is using this kind of block here, and this block is actually referred to OTA. So this is an operational transconductance amplifier. Okay. How to disable it? Okay. Oh, cannot remove that. Okay. How does it go? Oh, can you see? Okay. So this is a operational transconductance amplifier. So basically, operation OTA is often used in power supply because, according to what I hear, the implementation is somehow cheaper compared to operational amplifier, and so that's why it is favorable in many cases. And then the other thing is because OTA, the way OTA works is it sends what the voltage difference across the two input pin, and then it will generate proportional current at the output. So by using an OTA, it's actually a lot easier to perform the limiter function in this thing, right? So in the Qspice, we can use a behavior called constant, voltage controlled current source to emulate the OTA. And then because, of course, we don't want to have a unreasonable behavior of the OTA, so we have to put a limiter. But the good thing is, because this is the current source output, so we can just put a 0 here, and then our output will be limited at 5 volt. And so, okay, and then to implement the soft start, the way the soft start is implemented in this IC is by using a current source. So you can see there is a, hello, are you okay? Okay. Are you okay? Okay, let's move on. So basically here you can see that for the soft start, it is implemented using this kind of complex structure. However, if you pay attention to more detail about this structure, you can see that in this IC, the soft start controller itself is actually combined with the protection function. And anyway, because earlier I already mentioned that the advanced protection is not necessary for our case, so we can just not use any of those. So we can just X, and then for there is also this switch here that is used to control the protection function anyway, and we don't need that, so we just bypass this. So then the final result is much simpler. We just have current source, and then we put a capacitor here on the outside. Later you can see, and yeah, that's a whole compensation with the soft start. Okay. Next is how about the actual current mode, charge mode control implementation. So for the charge mode controller implementation, there are actually 4 important parts that we are going to see here. Number one is the internal slope generation. So similar to the current mode control, charge mode control also implement a slope compensation. However, and then in this IC, the slope compensation is used for 2 functions at once. One is to perform the slope compensation, and second is also to implement the minimum frequency limiter. So basically, the amount of the slope is programmable by using this external resistor here, and the way the way that this is implemented is actually by using, okay, you apply, so this pin here, the Fmin pin here will be constant at 1.5 volt, and then the current that flows through this Fmin pin will be mirrored to this current source. So then basically we just, to implement that, I don't need to implement the whole thing. I just need to implement a constant current source where the amount of the current is calculated as 1.5 volt divided by the resistor that I may be putting here. And so that's simply the whole slope generation. And then the minimum frequency implementation, the minimum frequency of this IC is controlled by using comparators. So once the capacitor voltage here reaches 3 volt, and the switch will turn off the primary MOSFET. That's it. And then, so that is the internal slope generation. And second will be the charge mode controller. So charge mode controller, the core of the charge mode controller is pretty simple. Number one, you measure the current through the resonant tank, and then from the measured current, you can measure the current using a current transformer, because current transformer is heavily used for this kind of application because it has incredibly high bandwidth, so you can handle up to a few megahertz easily and cheaply. Meanwhile, if you are going to use shunt resistor, the inductance effect will be too strong, and the signal is also very small, so it's not very easy to use. If you're going to use Hall effect, it's not as fast. So the way the charge is implemented, the charge is estimated is by using current transformer, which is then terminated using a burden resistor. So these RCS2 and RCS1 actually perform as a burden resistor, and then they just implement a voltage divider so that they can adjust the protection level, but it's not going to be used for us at all for this case. And if the voltage at this pin here is proportional to the current, then we can implement the integrator. In this case, actually, the integrator is implemented using low-pass filter with very low cutoff frequency. So actually, that is a valid method as long as your cutoff frequency of your low-pass filter is much, much lower, maybe 100 times or 1,000 times lower at least, to compare to the frequency of interest, or in this case, minimum frequency of your resonant tank, then your low-pass filter will behave almost as if it is a integrator. That's why here I just say resonant charge estimator. The actual resonant charge measurement is using a real integrator, but it's close enough. All right, and then after you estimate the resonant charge, then you just multiply with some gain, and then you take the total of the charge estimation with the slope compensation, then you can get basically similar to charge mode for current mode control. So the current plus the internal slope generation, and then you compare with some reference. That's it. So then you can get the charge mode controller. And then once the level of this total are above your controller output, then you turn off the primary switch. All right, and then the signal from these two things will be the way the minimum frequency implementation and the charge mode controller itself work is, under normal operation, the charge mode controller should be able to trigger the oscillator first. However, in case you have extremely big load where this one will never be triggered, so then at that point, the minimum frequency implementation will be triggered first, and it will force the switch to turn off. So that's how it will work. All right. And then the funny thing about this IC is, if you look at this picture is a little bit weird. So because you can see that, okay, the input current is sine wave. However, at this point, the integrator signal is only half. That is, after this one half, then it will be just zero. So this is actually by design, because the way they implement the charge mode control is not doing the charge mode control for the whole period of the switching period. However, it just do for half period. So when the upper switch is on, meanwhile when the lower switch is on, basically just duplicate the turn-on duration of the upper switch. So the lower switch turn-on duration is not controlled, just duplicate of the upper switch. I don't understand why they may be doing that, because another IC, like for example the charge mode controller from Texas Instruments or from MPS, they do the charge mode controller on both period, on when the high side MOSFET is on, and when the low side MOSFET is on. The only reason that I can think of why and on SiMi they decided to do in this kind of version is perhaps because it is simpler to do it. because you can do this part for the low side control using digital, and then I believe the chip size is smaller. And second is, if you want to do everything in the analog, you need to make sure that your circuit behavior matches 100% between the for the top side switch control and the bottom side switch control. And if you want to make sure that you can do 100% accuracy, I believe in the analog sense, it may cost a little bit more to do the calibration and everything. So yeah, I guess for the money. All right, let's go ahead. Okay. This part is a VCO and burst mode implementation. All right. So this is the part where it gets tricky, because in the data sheet, it just say, okay, when should we turn off the MOSFET? Okay, we should turn off the MOSFET if the internal slope reaches 3 volt, this CT capacitor voltage reaches 3 volt. And honestly, actually, they do not even tell me what is the value of the CT, so I have to deduce it by myself. And then it measures the PCOM, the whole oscillator here, it measures the PCOM. And then it sends the sum of the charge and internal slope, basically this to this pin here. And then when the compensation pin goes below 1.25, then it enters skip cycle or burst mode in another IC. And then when it goes above 1.3, then it resumes the normal operation. However, there are a few things that we can deduce from the datasheet by just being tricky. Number one, the VCO is a digital ASIC with a 40 megahertz clock cycle. They mentioned it that this one is working with a 40 megahertz sampling. So I believe the VCO is a digital ASIC. And then the output PWM is synced to a 40 megahertz clock. So what it means is, for example, when the integrator signal here goes above the PCOM, the compensator output, it will not immediately turn off the upper switch. Instead, it will generate the trigger and then wait until the 40 megahertz clock here do the sampling. And after that, it will turn off the MOSFET. All right. And then the charge mode operation occurs only on half of the switching period when the upper MOSFET is on. And then the lower MOSFET is basically just a mirror of the upper MOSFET. And then the implementation, I believe they implement it using up-down counter. And in the Qspice, I do not implement it with a real up-down counter because that will be pretty slow, but there is some magical C-block tricks that I can use there. And basically, the reset signal is an exact inverse of the upper MOSFET signal. So it will not, the reset will stay reset. We'll make sure that the reset MOSFET here is always on, even when the upper MOSFET is on the dead time period before it turn on. And then the dead time setting is directly taken from the datasheet. All right. So what do I mean by dead time implementation is taken directly from the datasheet? So in the datasheet, you can find this table, and then basically it tells us how should we decide the dead time for the primary switches and the secondary switches, and then you can adjust this resistor and capacitor so that using a certain combination, then you can get, for example, you want to have 200 nanosecond on the secondary side and then 100 nanosecond on the primary side, then you can use this capacitor and then this resistor if you want. But yeah, for the implementation, because the setting is only done during the startup of the IC, so we can just say, okay, I already choose what I want. So in my program, in my C block implementation, I do not have this RC implementation. I just say, okay, how much I want. That's it. Oh, I did not finish my sentence here. Okay, my bad. And lastly, there is a simplified SR implementation. So this is a super simple one. So you just put a shunt resistor and then you measure if the voltage in this pin is higher than the threshold. So in this case, threshold is 1 amp. So if the current that flows through here is higher than 1 amp, then you turn on this MOSFET. So the current will flow through the MOSFET instead of the diode here. That's it. Actually, this is not very necessary, but it works. All right. So next is we can have the transients simulation result, and believe it or not, I do not do any tuning for this IC, and it works fine. So that's one of the beauty of using this charge mode control. It's very simple to tune. And this one, okay, this one may be a little bit too slow for some of you, but I just replaced this capacitor with 10 nanosecond. It behaves the compensation capacitor and behaves a lot faster without any math. And then if you are interested with the frequency response behavior, then this is the result. So I modified the simulation a little bit. You can also find these models in my GitHub page, and you can see that I add the frequency response analyzer, and then we can get some wave measurement result, and then this is a bottom plot result. So as you can see here, that in general, for the power supply, for controller system design, we have a few goals. Number one is we want to have high gain, and the low frequency, which is already happened, is the low frequency gain is pretty darn high, and this one is it tends to go monotonously on the same slope. So at 100 hertz, this one is at this level. So at the real DC, it will be much higher there. And then crossover frequency, in this case, is around 2 kilohertz, I believe. And then the phase margin is around, I think, maybe around 60 hertz, 60 degree, which is perfect without any tuning. So yeah, this compared to the standard LLC controller, where you can have the resonant pole on the high frequency, and this one do not have any resonant pole, although it's a lot nicer to design with. And now we can move on to the simulation itself. All right, so how to hide this thing? Okay, so this is the simulation that I developed, and so how shall we start? Okay, so in this simulation we can, this is an LLC, obviously, and then in this LLC we can have so this is a primary site. The primary site is implemented using half-bridge structure, and then the secondary site here is implemented using a center tap rectifier, and then the output voltage is actually set at 12 volt. And the beauty of this circuit is because number one, this circuit using OTA, so the feedback structure is done by simply using a single capacitor here. And then, for example, now I just run this one, and then we can wait for the result. Yeah, so here you can see that the transient performance is a lot faster compared without any tuning. And then if I want, for example, to modify the system behavior, for example, I want to increase the switching frequency, and I don't even need to run any modification to my system, and it still behaves just as expected. Meanwhile, if you are working with a direct frequency modulation, then this kind of thing normally will not happen really often to us. So maybe we can do a little bit of probing to this circuit. So we can delete this part. Then you can. Okay, so a few things that may be easy for us to analyze about this circuit is, number one is there is a soft start behavior. So for the soft start behavior, we can analyze by checking the reference voltage, which is this pin, the voltage in this C3 capacitor, and then we can compare it with the feedback circuit and also the output of the controller. So you can see for the soft start, the way the soft start is implemented is by increasing the reference voltage slowly from 0. So, for example, if you click on this one, you can see, okay, the reference voltage is increased slowly, and then the output voltage also follows it pretty nicely. And then we can try, okay, the output voltage follows the slope pretty nicely, and then because of that, then the then the compensation signal also increase slowly. It doesn't go to very high level in an instant. And then the other thing that you may be interested to look at from this one is how about the integrator behavior?
Just
So the integrator circuit. Huh? Okay. Yeah, so the other thing you may be interested is to check about the integrated circuit behavior as well as the stop compensation behavior. So you can see here that this, okay, we can check the steady state. It will be a little bit easier to follow. Yeah, so this is a stop compensation. It's perfectly like this, and then as I told you before, that this thing only control when the controller only works when the MOSFET is on when the upper switch is on. So you can see here that, okay, this one only happened at one half of the period, and then the other half it will be just perfectly flat. And you can see, okay, we try to take the integral of the current. So you can see the current waveform is going up. So when the current is going up, then yeah, the integral, because it starts from the negative value, so it goes a little bit down and then it goes up, and then once it reaches a certain point, then it shut down the MOSFET in an instant. And then we can also do some probing. For example, we may be able to see how about the upper switch and the lower switch signal. Okay, so as I promised you that, yeah, this IC only perform the charge mode control when the upper switch is on. So you can see here that, yeah, when the upper switch is on, then you can see this integrator signal, but when the upper switch is off, then there is no such signal. And you can also confirm about the reset pin behavior. Click on this one. Yep. So when the reset pin, so for this one, you can use a probe. When the reset pin is off, then the start to turn off, then we can say, okay, the integrator start to work. And then after that, once it's reached the target, then it will turn on the reset. So then it discharges the integrator here and also this capacitor, and yeah, we will do the negative cycle sequence as a mirror of the positive cycle sequence. All right, and then what else? All right, so then next we can take a look about how I implemented this magical C block here. So this one can be a little bit too technical. Sorry, not very nice to look at. Edit with Notepad++. So this one is pretty much how what will you look at when you are opening Qspice. So there will be this template structure where you have this function defined, and then you can see this. This is pretty much a template. I'm not going to explain what those things are now. And then you can put all your variables inside this struct. So the purpose of doing that is to make sure that your data is the integrity of your data is maintained throughout the whole simulation, because in Qspice, the time step is not always committed, unlike a PSIM, for example. In PSIM, the time... sorry about that noise. I don't know what that thing is. Something next to my home. So in PSIM, if the simulation already commit to the next time step, the simulation always commit with the next time step. However, in Qspice, it will make a guess on how long is the next time step, and then if that guess is acceptable, then it will commit. But if the guess is not acceptable, then it will cancel that time step, move back to a smaller time step, and then try again. If it's still and then it will only commit if the condition is acceptable for all parties involved. So what I'm saying by that by the time is acceptable is because if there is discontinuity or there is some digital event like caused by some comparator or some C block, that it will force the simulation to refer to a smaller time step. And because of that structure, if you do not put your variables inside of this struct, then your variables value will be a big mess because you can do multiple iteration for the same time step if you're not careful. So you have to put your variables there. And as you can see, for that simulation, I just have, I don't know, this many variables for the implementation. And then here you can see about the implementation for the boost mode or the normal. So basically, it's simply compare the compensator comment with 1.25 or 1.3, and then if it's smaller, then it will enter the burst mode. If it's higher than 1.3, then it will not be in the burst mode. And then this one here is basically to tell about the positive cycle and negative cycle. It will control whether you need to turn on or turn off the MOSFET without the dead time. And then, so this will be the ideal switching time. However, because MOSFET in the real circuit needs some dead time, so the turn on signal is actually delayed, which is controlled by this part of the blocks. And then lastly is the VCO timing sampling. So basically, it will just sense if the slope compensation capacitor value is greater than 3, and then if it's greater than 3, then and then the MOSFET is not the reset pin is currently off, then it will trigger the timing to reset. Or if the charge mode controller voltage output is greater than the comparator reference, then it will also reset. That's it. So yes, that's pretty much the end of my presentation. It may be a little bit technical, but I think this is it can bring some idea on to other people on how to make their life easier with their work. Okay, I guess that's all. Maybe somebody wants to ask me anything.
Yeah.
Go ahead.
Thank you, Dr. Aref. Anyone have any questions? So can raise your hand. You can speak directly with Dr. Aref. Okay, I can have question to you. First is, could you tell me about what is you mean a charging mode controller in here? Is this include the burst mode plus with the frequency control? That means some sequence or yeah, you say many things about the charge mode. Could you explain to me a little bit about that?
Okay,
Charge mode
so
control, what is different compared with the frequency control? What is yeah.
all right. So okay, maybe I can open a little bit about the how to hide this thing. Oh, I can move it simply. Okay. Let's see. So you might be familiar with SIC if you work with a resonant converter. Anyway, this is one of the very famous LLC controller, right? So basically, let's go to the VCO section directly. Okay, oscillator. Let's go to that section. Please wait. All right. So okay, so this is an oscillator of this IC. So the way this oscillator works is by having a fixed comparator on this timing capacitor, right? And then the how is this capacitor is being charged? I mean, because the way we charge this capacitor is by applying current to this capacitor or by discharging with some constant current out of this capacitor, right? And the rate of this charging or discharging is controlled by how much current is flowing through this path, which is controlled by your controller. where you control, you can see here on the bottom left here, this one is optocoupler. And if you apply more current in the diode side of the optocoupler, then there will be more current flows through here. If there is more current flows through here, then the current that will charge and discharge this capacitor will be a lot bigger. And if the current is bigger, then it will swing between 0.9 to 3.9 faster compared to if you have smaller current that charges the capacitor, the timing capacitor. So basically, this is how the direct frequency control. So you sense the output, and then you directly control how fast you want to charge or discharge your timing capacitor. However, for the charge mode control, the way the controller works is by the compensator does not tell you how fast you charge or discharge your timing capacitor. Instead, what it will do is, let me see, Susan showing. Instead, what the controller will do is it will only tell how much, oh, sorry, I have this one here. It will only tell you how much voltage of this gap in should be before you turn off the MOSFET. So, for example, here, let me see where can I put it. Okay, so here I can click this signal here. Now, so let me see which one I can remove. I can remove you. I can remove you. Yeah, go up. All right. All right. So the difference between the direct frequency and charge mode control is the controller command here. Okay, if you see this COM pin here, the controller command, it tells at what charge level that you should turn off your MOSFET. It does not tell you that how quick you should you charge or discharge. Instead, it will tell you at what level should you switch your MOSFET. Does it make sense to you?
So I just want to ask about what is the purpose of the charge mode control. Is this a burst mode control? What's the difference with burst mode?
No, this is a normal operation.
This is in normal operation, not in the start.
No. So the purpose of the charge mode control is, at the beginning, I have mentioned that you may be familiar with voltage mode control and current mode control, right?
Mm-hmm. Yes.
Yeah. So voltage mode control, basically, for power supply, if you know how to work with current mode control, you want to avoid the voltage mode control, right? Because the transient behavior is a lot better. Correct?
Right. Yeah.
The transient behavior, and then the switch, basically the control performance is better. Correct? Now, so then basically where the charge mode control is also developed for the same reason. So direct frequency control is implemented for the, what's it called? The direct frequency control was developed first, and then people think, okay, the transient behavior is not very nice, and then the system is pretty much sensitive towards the load variation and also input voltage variation, and then they can figure out that they can do charge mode control, which somehow magically it behaves a lot more similar to the current mode control in the PWM converter. So then by using charge mode control, your transient behavior is a lot nicer. And then the number one benefit is it is a lot easier to tune the charge mode control LLC for the the controller tuning. And then number two is similar to the current mode control, where current mode control has the input voltage feed-forward characteristic. So basically what it means is if your input voltage suddenly increase, your output normally will not change significantly. So charge mode control also have that kind of behavior. So if your input voltage suddenly increase, then your output will be more stable, which is pretty useful, for example, in a power supply application where the input is supplied by PFC. So when you are having your input is supplied by PFC, then your input voltage will not be perfectly flat at 400 volt, right? Your input voltage will have some oscillation. And because this one can have that input feed forward characteristic, so your output voltage ripple will be a lot flatter without any complicated tuning. And third is, what is it? Oh, the behavior
right,
does
yeah,
not
yeah.
affect.
I almost got the idea. Yeah, yeah. So
Yeah.
yeah. Thank you for your answer. Yeah, maybe I after this meeting, maybe I can contact you to ask more because we don't have
No
time
problem.
here. Sorry. Yeah.
No
And then we
problem.
have one more question, two more questions, three more questions.
Uh-huh.
Sorry. Yeah, we don't
Yeah,
have time,
sure.
but yeah, you have 5 minutes to answer. The question from anh Tưởng.
Yeah,
Yeah.
I'm Tưởng, a web engineer. So I have a question regarding to the model. So normally for LT Spy to create the simulation, have to use model from manufacturer, for example TI, ADI, and to create the model for myself for the datasheet chip. If not available, I cannot simulation. So I see here that you can create by yourself. So yeah, so my question is that all programmable or you need to using some block like in LT Spy?
Oh, so if you see here, then basically you can see that this part are just block, like, I just close this one. So this part are just blocks similar as you can find in the LT Spice. However, the thing that is not available in LT Spice is this one. This is a C block. So you can make the model whatever you like in this way, and then you can check if the result is as what you expect. So if you are trying to make digital control, it's a lot nicer. In fact, I made a lot of digital control simulation for my other work. So for example, if you look at my presentation, at the beginning I show about that totem pole PFC that is part of my work, and that thing is actually will be implemented in the MCU. So this one here. So yeah, so basically using the C block, you can do some logical implementation a lot easier compared to the using the blocks. Yeah.
Yeah, maybe at the seminar, I will take a look at your link and reuse your model to
Okay.
our
cool. Cool.
Thank you.
Yeah. Okay. So maybe we should answer this question first. I have a question for you that does the charge mode can help LLC increase the frequency response compared to the normal control? In my experience, the transient performance is a lot better. So yeah, that's it. And then for this one, yeah, I can get that very nice circuit behavior with just simple type 1, which I don't think it's attainable with the the frequency, direct frequency control LLC. And then second is, thank you. But why can it simulate the whole system in very fast? Basically, I don't know the actual answer. I mean, I'm not the one who makes the Qspice. However, in my understanding, why it is a lot faster is because for the Qspice, the solver, the actual part of the program that actually handle the circuit simulation is modified significantly, where it now can handle the switching much better compared to LD Spice. And then second part is if you can, and second part is the C block in the Qspice can do the timing manipulation. So you can actually influence the time step, the simulation time step directly from the C block. So yeah, if you open the Qspice forum, there are a few discussion about that, and I also initiate that discussion. And anyway, yes, of course, one more question. I mean, depends on the moderator, but for me, it's okay.
Hi, I'm Huy. So I ask you about, and as you said, the chalk mode can increase the LLC frequency response compared to the normal control. So I want to ask how you compare the behavior between the chalk mode control and the normal control.
I haven't run the whole simulation for the normal controller, but from I see from the literature, if you let's look at the frequency response characteristic here. So if you look at this one, so the one thing that is very annoying for the normal controller is, number one, the border plot for different load and different input voltage change a lot. Okay. And then number two is for the number two is, okay, there will be a pole, how to say this, resonant pole in the output side here in the high frequency, where if you are using the, what is it called, normal LLC control. And somehow, to my understanding, for charge mode control, which is similar to current mode control, the double pole at the high frequency happens at much higher frequency, so you don't need to care about that resonant pole anymore in most design. And by having that behavior, number one, it is a lot easier if you are working with system that need to operate under wide operation condition, for example, like a charger. Number two is you can tune your controller to have higher switching, higher crossover frequency, because you don't have that resonant pole. Because if you have a resonant pole, then you have to make sure that the peak of your resonant pole is below 0 dB. But if you don't have that resonant pole, I mean, that resonant pole is at extremely high frequency, so you can ignore that. So if you don't have that resonant pole, then you can increase your crossover frequency higher. And if you can implement higher crossover frequency, then you can have faster transient response. That's my understanding.
Okay, thank you very much.
You're welcome.
I'm sorry, we're almost out of time. So yeah, we left one more question. Is the download? Oh, okay. Not that question. Okay. But we out of time. So here we have question from Tiep. But maybe Tiep can contact with Dr. Arif after this meeting. Is okay? Is this okay? Or after this? Yeah, we are waiting for the other presentation.
Okay,
Yeah,
sure.
so
No problem.
yeah, we have many questions actually. I also have many questions, but I don't have time to ask. Yeah.
No problem.
Okay,
We
thank
can
you
find
for
one.
your interesting topic. Yeah, that is Qspice is really new to us actually. I know that is really developed from the Cubo, maybe, right? Yeah, and then yeah, we've been looking, and then we try to run your simulation. You share already. You already share your GitHub link, right? And then maybe
Yes,
everyone can download.
All
That's
right.
good.
Sure.
Yeah.
Okay.
Thank you.
Okay. Thanks a lot.
Thank you, Dr. Arif. Yeah. So.
Okay. Have a good day. Enjoy the weekend. Bye bye.